Hello, everybody. Thanks for joining this session. So the topic of the session is how to get realistic C-state, latency, and residency figure for your platform. So I will start with an overview and a reason why we have decided to work on that. And then we'll explain how we can easily compute, exit latency, interlatency, and the residency time, which are the three main tunable for your C-state. And then we will conclude according to the results. So the overview. So in our PMWG team, which is the Power Management Working Group, we are using the HKG18-111 for our development on big. LITTLE system. And when you look at the main line, or I think even for the Android command kernel, when you look at the residency state value, so that's the one I have put there, you can see that the residency time, for example, for the cluster of state is set to 20 milliseconds. So the first time that we have seen that, the value were looking really high compared to what we used to have for other chipsets. So we decided to find a way to check are these values were correct or not for the platform. So that's why comes this topic on how to get realistic value on my platform. So the goal is to do that without expensive materials because we don't have access to such materials. Also without having deep knowledge in the power management and how to interpret the result. And also, so the goal was either to define some value for a new platform or to check the current value in the DT binding. So the C-state latency, this is the first step. So how it's defined in DT binding, so we have three values. So the C-state latency is split in three main values, the prepare, the entry, and the exit. So the prepare, it's something that can abort, and it's mainly doing some maintenance, like cache maintenance, flushing the cache or everything else that can be done before really entering the hardware state. So it's abortable. We then have the entry step, which is both made of hardware and software sequence, where we will configure and tune the PMIC or whatever, your PLL, whatever need to be shut down or need to be prepared to shut down. And normally this sequence is not abortable. And after that, we will enter the idle C-state that we have selected. And then we have the exit latency, which include everything that need to be done on hardware and software in order to bring back the CPU to the correct running state. So how to measure the latency? The goal for us is to look for the worst value. So we need to trigger all the possible contention when we are doing the measurement and making sure that the CPU will compete for accessing all the critical resources in the path. If you have any software lock or hardware lock or whatever that is shared between the CPU, the goal is that to make sure that all the CPU try to access that at the same time. So they will have to wait for each other to get access. And also, we want to make sure that we will trigger the slowest path, which means that we will use the slowest path for each step, like flushing the cache. If you have to flush only one line or all the line of your cache, the duration will not be the same. So we want to make sure that we will have a use case where we will flush most of all the cache for the best case, or at least most of the cache. So for testing, for doing our measurement, we are using several software features. So we have done that on the HKG18-111. And so for our measurement, we have modified the board to get access to the 4.2 voltage domain. But we'll see a bit later that it's not really necessary. It's just that we have done that on our board because we are really interested by the SOC power consumption, and we don't want to be disturbed by any Bluetooth, Wi-Fi, or USB activity. So that's why we have done that. We are using an ARM energy probe, which is a USB dongle that enables you to make some power consumption measurement on 3 channels simultaneously. but I mean, we have chosen this dongle just because it was available in the team. There is no other reason than that. So you can use almost any other kind of energy measurement device. So for us, the goal is to isolate the CPU that we want to test from any external activity, noise, background, task. And for that, we have used the isol CPU feature, which is available in the kernel. So the feature was working really great on the big cluster. So with the command line, where with putting isol CPU, CPU 4, 5, 6, and 7 on the HKG18-111, there was no activity on the big cluster apart from what we were pinning on them. For the little cluster, it was not that great, mainly because the boot CPU is a little one. So a lot of things are pinned to this CPU when we are booting, even before the isolation starts to work correctly. And also, by default, all the interrupts are pinned to the CPU 0, which means that some tasks, some timer activity will also be pinned to this CPU. So that will generate some activity that we can't easily remove. So the best way to do that is just to move all the IRQ on another cluster, and then to unplug and replug all the CPU one by one. But even after that, we still have to move some tasks manually. So that's maybe something we'll have to look at later. And for the test case, we have used RTApp, which is an application used to test the scheduler mainly. So it's using some JSON file to describe the behavior of the task, when you want to wake up, how long you want to run, if you want to sync the wake up of some task. And you can specify different kind of dependency between the tasks. And you also have a log of all the events and how much time you have spent in the different step of your use case, which was useful for us. So the first measurement that we have done is the exit latency, which is the simplest value to get. So for doing that, we are enabling only one state for the CPU that we want to get the value. That can easily be done with the CCFS interface, where you can use the disable entry. During the test, we have seen, in fact, it's not fully 100% robust in the sense that we have been seeing some spurious wake up on this from time to time. Let's say maybe 1 or 2 times per minute. And it's probably because some software, some interprocess interrupt was sent on all the CPU in the system for whatever the reason. But that's not a big problem for us because it was really few times during the test. So for the test, what we were doing, so we were putting all the CPU that we want to measure in idle, and the goal is to wake up all this CPU at the same time with a timer. So we are using an absolute value, so we are sure. Yeah?
What C state was this in? This is not cluster.
No, for this example, no, it's just to show what we want to do. But we have measured for WFI, CPU off, and cluster off. No, it's just to show that we are using a timer with RTApp that ensures that all the CPU will be fired at the same time. Then we are measuring, so then we need some time to wake up. And then we are reading the clock, the absolute clock, to see how much time we have spent to wake up. So the RTApp application logs this wake up latency, in fact, automatically. So you don't have to do the measurement is done by the application. And from this value, we can get the minimum value, the max value, the average, and some standard deviation that give you some statistic about how often you are at min or max. So I was running that for 1 minute, in fact, which means that I was able to run several thousand of wake up. And then I can display all the wake up latency. So on this chart, you have on the left the wake up latency for the cluster off of the big core at the lowest OPP, and on the right, it's at the highest OPP. So the dig part is where the time we need for 95% of the time, and then you can see the min and the max value. So the first interesting things to see is that one CPU always wakes up faster than the others. From one test to another one, the CPU can be different, but you always have one that wakes up faster. Most probably because it's the first one that gets one critical resource at the beginning, and the other one are just waiting for the end of this part. So you can see a difference between the highest and the lowest OPP, but not that much. We are around a bit less than 3 milliseconds, so it's microseconds. But most of the time, it's not really linked to the frequency of the CPU. But it's probably some hardware stuff, pouring up some power domain or syncing some, locking some PLL, something like that. This one, another interesting thing there is to see that, no, it's for the big core. We'll see that after for the other one. And this is for the CPU off state. So you can see that like the other one, so one wake up always faster than the other one, which can be a bit strange because normally they are not, there is no hardware dependency because it's per CPU in this case. So it's probably mean that the lock is a software lock. I don't know which one. Maybe the ATF, maybe somewhere else, I don't know. But on the previous one, we could assume that it was a common power domain, for example, or voltage domain. But for this one, normally they are fully independent. But we can even see some differences. And we can also see that between the max and the lowest OPP, we don't see that much difference in the wake-up latency. So that's the summary. So as I explained, we have one CPU that wakes up faster. So it probably gets a critical resource before the other one. I haven't showed that, but we can see that the frequency of the other cluster, so in this case, depending if the little core was running at the lowest or the highest OPP, it was impacting the wake-up latency of the big core. And running the other cluster, the lowest frequency, was flattening the wake-up latency, whatever the frequency you were running on the big core. So at the end, yeah, so for example, there was 400 microseconds of difference when the big cluster was running at highest OPP, depending of the frequency of the little cluster, which can be significant. And yeah, the local frequency has a limited impact at the end. It was only 200 microseconds across the 2,900 microseconds of full wake-up latency. And I have also tried to wake up all the other little cluster at the same time to see if there was some dependency, but the difference was almost a few dozen of microseconds, which means that there is no real link in this case. Another important thing that we need to take care is the firmware that you are using. If you are using the debug or the release version, you can see more than 200 or 300 microseconds of difference. Which means that, so yeah, at the end for the, so I have put all the results there for the big and the little cluster. So for the big cluster, we can see that we are a bit less than 3 milliseconds to wake up in the worst case. And for the little cluster, it's only 1,600 microseconds, which means that the little cluster is faster to wake up than the big. Yeah?
So how do you actually verify that you built the cluster power down?
Yeah.
How do you actually?
With the ARM energy probe, I'm able to see that the power consumption is changing, yeah. So yeah, the fact that the little cluster is much faster than the big probably means that more hardware are down for the cluster, for the big cluster compared to the little cluster. We are doing more things. We can see that for the CPU off state, it's almost the same. And for the Wi-Fi, we are a bit lower than 100 microseconds for the big cores and 100 microseconds for the little cores. So just to remind that what we are measuring there is the time between we are firing the timer at a defined absolute time. Then we have the PM coprocessor that wake up all the hardware things, regulator, whatever you have to do in hardware. Then we have the ARM trusted firmware that resumes the sequence for the cluster and the CPU state, but not for the WFI state. Then we are running the CPU idle driver, then the CPU idle framework. We go back to the idle thread, then switch back to the RT app, waking up the tick, and then reading the time clock. So that's probably why we have that much value for the WFI. It's not just waking up the CPU. It's waking up the CPU and switching back to the RT app thread. So we can probably save few dozen of microseconds there. But if you come back to the previous value at the beginning, for the big cluster, the exit latency for big and little was set to 5 milliseconds. And here, the measurement we have is almost half, or even less than that. So for that, it just I have a shell script that run automatically and provide you all the results. For the entry latency, it's a bit more difficult to find a way to compute that, because you can modify your code, set some GPIO when you are entering or going out. You can do a lot of things, but the goal there was to do something simple to reproduce without without a lot of material. So for that, we are still using the RT app, and what we are doing in this case, we are increasing step by step the time spent in sleep duration. And what's happened is that when you want to sleep a really short time, so the timer fire when you are still in the prepare sequence, for example, so you can abort that, and you wake up immediately. And then you are increasing time by time the sleep duration. But at the end, the measurement should be the same, will stay the same, all this for all these three first cases. And once your sleep duration starts to be higher than the entry and the entry latency, you will start to see the increase of your sleep sequence. So this is a chart that shows the sleep duration, not the sleep duration, the RT app phase duration. So the time to run 1 microsecond, sleep an amount of time, and then run 1 more microsecond. So we can see that at the beginning, even if we are increasing the sleep time, at the end, the value, the sequence stay the same. And only around 800 microseconds, we start to increase the run cycle. So which means that the entry latency is around 8 microseconds for this case. So this is the result for only one CPU. And so you can see some spike there from time to time. So when I have a look at the detail with some kernel shack trace, this, in fact, was caused by some USB activity that was waking up the CPU just before doing the test. So that's why it's so long. So we can discard that. It's really about this value which are interesting. This sequence has been done with all the CPU in the same cluster. And in this case, we can see some state there, which probably means that we have several abort points available, so around 900. And probably there, according to the value, it's probably that we are able to abort part of the wake-up latency. Or in the hardware path, we're able to skip some phase. And then after this value, the 1 and 9 milliseconds, we can see that we start to increase linearly with the sleep duration.
So if the sleep duration is less than the NK latency,
Yeah.
we shouldn't be going to sleep, right? We check for that as part of the break-even cost.
Sorry, if we?
We check for that as part of the break-even cost.
Yeah.
Going into an idle state, right?
Yeah.
So it shouldn't actually be going to idle.
No, we're not going to idle, in fact. Sorry. In this case, it's there. So as long as you are there, you are not going to idle, but you need to go to make the prepare, entry step, exit step, which is constant. So that's why we have this step. And once the sleep duration is longer than the entry, the prepare and the entry, in this case, we can see that the full round is increasing linearly. So these are the results for the big and the little cluster. So we have a bit less than 1 millisecond for entering the cluster state. In the worst case, 500 microseconds for the CPU state for the big cluster, and the value for WFI was almost, yes. I mean, the step that I was using there was I was increasing the sleep duration by every 100 or 50 microseconds, I can't remember. And it was almost, at the first step, we can see this increase. So it means that in WFI, which makes sense for WFI, because we don't have anything to do. So this is the final value for the big and the little cluster, for the entry and exit, and for the wake-up latency, which are different from the one that were set, that are set in the current C-state table. So like the previous one, I'm using a script that's running everything automatically and provide you the result at the end. Or at least the data to create the chart and see the break-even point.
Did you do an energy comparison before optimizing and after optimizing to see how much it
I have done that for some use case. I will speak a bit about that a bit later. The last value is the C-state residency. So the goal for the C-state residency is, so the residency time, it's the minimum time, the minimum idle time above which it's worth to enter this C-state compared to the previous one. So the goal, we are using the estimated idle duration, which is provided by a CPU idle framework. And based on that, we are looking for the C-state with the longest residency time. So we are trying to enter the deepest idle state. That makes sense. And of course, according to the wake-up latency constraint, we can skip some C-state. So how to estimate the residency time? The first solution is to measure precisely each step independently. The prepare state, the enter and the exit state, the idle state. And once you have all these values, you are able to compare and compute what is the break-even point between each state. But for doing that, you must have access to each port domain independently to make some really precise measurement, even more because all these states are transient. So it's quite difficult to catch them exactly. It's possible, but that often means to have some expensive materials. Whereas at the end, we don't really care about the value. What we want is to compare C-state between each other and see one is better than the other one. So for that, what I have done, so I'm still using RTAP, and I'm waking up the CPU periodically with a always shorter sleep duration. So the task that is waking up on the CPU doesn't do anything except waking up and go back to idle, so that the power impact is really linked to the enter and exit latency. The goal is to run the same number of wake up and sleep for all the C state, for all the periods, so you can compare. So that at the end, you just have to compare the result instead of trying to measure. So yeah, you don't need the absolute value, but just to compare the result. And because we are comparing the result, you don't need access to the power domain for each power domain. You can even use the whole power supply if you have only that. The main difficulty is that you will have to make sure that the background and noise activity will not disturb too much your measurement. So I'm using RTApp to generate this wakeup, periodic wakeup. So from 10 milliseconds to 1 millisecond with a step of half a millisecond. For the other cluster, in order to minimize the noise, so I keep the other cluster in WFI and lowest OPP. So if there is any wake-up, spurious wake-up on the other cluster, that will not impact that much the power consumption. And I'm running that for at least 20 seconds and 8 times so that I can filter any noise, additional noise. So this means that for the HKG18-111, for example, in this case, I need more than 3 days of power consumption measurement to get all the value. And at the end, what we have is something like that, some chart. So this is the power consumption for the 3 states of the big cluster. And so on the x-axis, it's the wake-up period, or the sleep duration. And the y-axis, the vertical axis, is the power consumption. But we don't really care about that. So the orange one is the WFI. You can see that it's quite stable. Waking up doesn't have a huge impact. The red one is for CPU off. So we can see that when we use really short period, the power impact starts to increase exponentially. And the blue one is for the cluster off. So with this chart, we're able to see when it was to use the CPU off instead of the cluster. Because we can see that if we are waking up in less than 5 milliseconds, the CPU state will be more useful than the other one. And this break is where we start to have a sleep duration that is shorter than the entry and the wake-up latency. So we start to run less number of loops. That's why it starts to decrease. And there, for the red and the orange, is the break-even point between WFI and CPU. So this was at the lowest OPP, and this one is for the highest OPP. So, sorry? It was, I thought there were no session after. Oh, sorry. Yeah. So this is the value. The main conclusion is that the residency time is quite different depending on the OPP. If you're using lowest OPP, which can make sense because if you're using lowest OPP, the static power consumption is really small between cluster off and CPU, whereas at highest OPP, the difference it's more important, so that's why. And that just raised the point that we might need to weight the residency state with the current OPP of the CPU. And the conclusion, so yeah, I have run more RTApp tests on that, filling some memory instead of just working up the CPU, just to fill the cache. So the OPP has a significant impact on the residency time. The script will be available soon on the website, and the next step is to automate all the chart creation and value extraction. And on Wednesday, we have a follow-up on this session during an hacking session if you want to go more deeply in the detail of the script. And that's all. Thank you.